Alright, my name is Jack Wampler, and today I'm going to be talking about our experience running refraction networking in production. These are my co-authors and some of our partners from along the way. So, censorship on the internet is a global problem today, affecting the free flow of information and journalism around the world. Now, one of the most common ways to get around censorship is using something called a proxy or a VPN. And what this allows users to do is connect to a host external to the censoring network and tunnel their traffic so that the proxy host makes requests on their behalf, allowing them to access content that would otherwise be blocked. Of course, censors are always looking to block these proxies as well, and they can do this by IP or using the domain name system, using and abusing the domain name system. But one way to escalate this game in favor of censorship circumvention is to use something called refraction networking. And what refraction networking does is it moves the proxying logic into the center of the network. So now a user who wants to use a refraction networking proxy connects to a host that is unblocked, where their traffic routes past the proxy in the middle of the network and includes a tag such that the proxy can identify the flow and forward it to the censored content that the user wants to access. And if the censor were to inspect this flow, what they would see is that the traffic looks like it's coming from a site that is allowed to be accessed. Now, refraction networking, formerly known as decoy routing, has been around for around a decade now as a research topic, and there's a bunch of different refraction schemes. But in this work, we're going to specifically focus on tap dance, because that's the refraction scheme that we ended up deploying. So early refraction schemes relied on something called inline blocking. What this required is that refraction proxy station would be deployed at a router. And when a client connects past the router with a tagged flow, the router would drop the connection and redirect the traffic to the covert host that the client wanted to access. Now, this was not particularly deployable because partner ISPs were concerned that integrating inline blocking devices into their network is dangerous in the case that a station crashes or interferes with other traffic in some way, so they're hesitant to put inline blocking mechanisms to support refraction networking. So, enter TapDance, which was specifically designed with this in mind. So, instead of working inline at the router, it listens to a copy of all the packets that go past a router on what's called a passive tap. So, when the client connects to a decoy site and their traffic routes past the router, the refraction station gets a copy of those packets and is able to operate on that. So the client then sends something to prevent the decoy from responding. In our case, this is a TLS session where the client sends an incomplete HTTPS request. The decoy site's going to wait and wait for the completion of that request, and in the meantime, the client can keep sending data, and the refraction station can ferry traffic to the covert site that the client wants to access and spoof responses as though they're coming from the decoy site. So this is the architecture that we deployed, and we've been running TapDance for around 2 years now, though in this work we're going to evaluate specifically 4 months of data from early 2019. Now, our deployment relies heavily on our partner internet service provider, Merit Network in Michigan, which services many educational institutions. And we deploy 4 stations at routers placed at ingress points in the Merit network. And 3 of those are at 40 gigabit per second routers, and 1 is at a 20 gigabit per second router, for a total of 140 gigabits per second max capacity that could be flowing past those stations at any point. Now, in practice, we did not see that much traffic flowing past those routers. Typically, those routers in Merit's network had accumulated around altogether 70 gigabits per second at any given time. And that's just the normal ISP traffic that Merit manages for their customers and mirrors to our taps for Refraction to operate on. We are specifically concerned with TLS flows, so you can tell here that the number of TLS flows checked at any given time varies directly with direct proportion to the amount of traffic that's going past. The architecture that those stations operate in is structured in this way. So we have at the passive taps, at each of those 4 passive taps, a detector that listens for the tagged flows. And when any one of those detectors finds a tagged flow, it forwards it to a singular centralized proxy manager. Now, what this allows is if a client needs to multiplex their connection over more than one connection, say it gets cut short, then they can connect past any one of the different refraction detectors or participating routers equivalently, and their session will be routed past the same refraction proxy, and the multiplexing is easy. This was something we developed from one of the very early trial deployments in 2017, and this is the architecture that we have deployed and have continued to run in deployment even now. So, multiple detectors stationed at routers in Merit's ingress points feed traffic to the proxy manager, which then manages the multiplex sessions and connection to the covert endpoints. And from each of these, we collect logging. So from the detectors, we collect logging information as well as from the proxy manager. And we also allow clients to send performance statistics in the transport to the proxy manager as they're establishing their connection. So this would be things like round trip times, connection establishment latency times, and failed decoys. These are important for evaluating the performance of the Tapdance network as a whole. So the next big piece of the Tapdance system are the decoy sites. We collect these decoy sites by port scanning port 443 across the entire Merit address space. And this provides us with a list of all of the available TLS hosts that could potentially be used as they route past Merit's infrastructure where we have our stations placed. We then filter these down to include only compatible decoys. And we filter for a couple things, but one good example is we filter for specific TLS cipher suites because Tapdance requires the use of one of a few commonly supported TLS cipher suites for the tagging system that it uses. A second thing that we filter for is, has this decoy requested to be excluded in the past? In the traffic that we send to each of the decoys, we include a notification that they may include a piece of text in their robot.txt, and we will exclude them from any future inclusion as a decoy in the Tapdance system. And so a few decoys did do this and opt out, but it was only a handful compared to our usual 1,500 to 2,000 decoys that went into any given configuration file. Now, the final piece is the clients. We need clients to be using Tapdance and connecting to the system. And the way that we went about doing this is by integrating with the Siphon proxy Android application. And this allowed us to include around 600,000 users in censored countries around the world to test the success of the Tapdance system. And now the way that Siphon works, they actually connect to a number of proxy transports in parallel, such that the one that connects fastest or is most performant is used by the client. So in this way, Tapdance competes with the other proxies and supports them should any of the others be blocked. Some of these other proxies include things like Meek, which is a domain fronting protocol, and obfuscated SSH, which is a randomizing direct protocol. Siphon also includes other direct proxy protocols in its horse race, as they call it. So the system altogether looks like this. We have our client integrated with the Siphon Android app, which sends traffic through the Merit network to the decoy sites that we discovered in our decoy discovery process. When tagged flows are detected by the detector, they are forwarded to the centralized refraction proxy, which then sends them to Siphon's backend endpoint servers. From there, Siphon manages the tunneling of traffic on the client's behalf, limiting clients to maximum 1 megabit per second bandwidth for any given user at any given time. So, looking at performance of the system as a whole, for all users combined of the Tapdance system, we typically saw around 250 megabits per second throughput. And for any individual user, we saw about 100 kilobits per second throughput. And as for that client experience for any given single user, to get connected to the Tapdance system, there tended to be a relatively high connection establishment latency, between 5 and 6 seconds typically. And we looked at all of the checkpoints in the Tapdance session establishment handshake, and we came up with the reason being that if a client fails to connect on their first try, they incur a high latency penalty because they have to try the whole handshake over again. Now, some reasons that they might fail are things like the decoy that they chose was down, or did not route past a participating router on its path from the client to the decoy for some reason. But either way, if the client failed that first handshake, they would have to retry the entire handshake, and that was a high penalty. As far as how those decoys are used, we hope that our decoys would be used uniformly, allowing connections to be balanced across them. In practice, that's not exactly what we found. We found that based on the number of sessions, the number of bytes, and the total duration that any decoy was used, about a third of the decoys were the most heavily used decoys, or the most relied upon. And if we look at some of the different distributions, a median decoy would expect to have 0 to 1 concurrent connections at any given time, whereas a decoy at the 99th percentile of usage, which is the blue line here, would expect to have between 10 and 20 concurrent connections at any given time. So some decoys definitely worked harder than the others. But even with this, the hardest working decoys were not overly burdened. Here we have the top 10 ranked hardest working decoys based on the mean concurrent connections. And you can see that all of these decoys serviced an average of about 1 kilobit per second, which is a definitely manageable amount of traffic. None of these decoys were overly burdened to the point where they, for example, opted out of inclusion in the Tapdance system. As far as our effect on our proxy partner, quick reminder, Siphon opens all of those proxy connections in parallel and then uses the one that is established the quickest or most performative. And in terms of bytes transferred, Tapdance represented consistently around 10% of the traffic that Siphon serviced overall. Interestingly, this performance lines up almost exactly with the number of users that we saw at any given time on the Tapdance system over these 4 months. And there were some interesting events throughout that time. So on January 3rd, some domain fronting methods were unblocked for a short period of time in a censoring country, and the number of users that chose Tapdance in the Siphon system dropped because domain fronting was quicker to connect to. That was only for a short time though, so those users came back to Tapdance when those methods were reblocked. On March 5th, some direct proxying methods were unblocked. And again, this is quicker to connect in a direct proxying method. So again, Tapdance saw a decrease in the number of users that were showing up in the Siphon proxy. But then on March 15th, direct and domain fronting were blocked in one of the popular censoring countries that Tapdance was useful for. and we saw a big spike in the number of users that were able to connect, or were forced to connect using Tapdance. Finally, on April 15th, we saw a new technique for censoring proxies that had previously been reliable for a long period of time, which many users were relying upon. And because of this, around 10 to 15,000 new users showed up to the Tapdance system on April 15th. So we were wondering, did this have a big effect on the way that the Tapdance system performed? Would you expect to see a difference in the traffic just because of the number of users that showed up? And it turns out that not really. Tapdance supported this surge in the number of users without a significant change in the session size or the session duration. So without degrading service, we're able to keep these users online in the event of a novel censorship strategy. So, some lessons that we learned from this. Tapdance is clearly useful. Refraction networking has a high value. However, there are some definite shortcomings to the Tapdance system. One obvious one is that selecting decoys is difficult. If a client chooses a decoy from the client configuration, and that decoy does not route past a participating router, whether that's because this decoy has a second upstream internet service provider and the traffic didn't ever go through the Merit network, or the decoy site was down just due to churn on the internet. If the traffic didn't go past a participating router, then we can't proxy it. And predicting that routing is difficult. So we classified how often clients could expect to fail this handshake. And it turns out that they typically expect to fail once per connection. So on average, a client would expect to connect, fail once, and then reconnect, and be able to connect to the Siphon to the Tapdance proxy using Siphon. And this again had caused those significant latency in establishing connections. A second drawback is tied pretty centrally to the way that the Tapdance system establishes connections, where the client starts a TLS session and then keeps it open. Because decoy sites are not typically known to allow connections to stay open for long periods of time, especially while the clients are uploading data to them continually. So these decoy sites will often, after a fixed period of time or a fixed amount of data, reclaim their resources and terminate the connection, forcing the client to open a new connection. And this is the reason that we had originally chosen to multiplex sessions across many Tapdance connections. But going forward, this is something that we needed to fix, and we've gone through a couple of iterations now and some engineering rabbit holes to get around this and design refraction networking in a new way. One of those was the idea of split flows, where we have two flows, one upload and one download. If the upload flow was closed, you would just open a new one. This didn't see a long deployment because of the intensive complexity. But we then were able to come up with the design specifically motivated by this trial for Conjur, which is the latest refraction networking design and removes a lot of the drawbacks that we saw throughout this trial. So, addressing some of our partner concerns, ISPs that we had talked to were concerned that there might be impacts on their production environments, whether that be affecting downstream users or overwhelming their network. We didn't see this at all. We had a manageable amount of outgoing traffic, and anytime a station went down, it never interrupted the function of our ISP partners. We also did not overwhelm any of the decoys that we used, and did not see a significant decoy attrition where they opted out at such a rate where Tapdance was no longer usable. And we continue to monitor the usage of these decoys. We also did not see any retaliation against the censors against the service providers by censoring countries. So overall, Tapdance had real-world value in unique, novel proxying events. Though it sees some challenges in selecting decoys, in upload and session duration performance, and also in scaling that are to be addressed in future refraction networking strategies. So with that, I'd like to thank my collaborators and all of our partners, and I'd be happy to take any questions.